In this video, I will talk with you about signal analysis and synthesis using Fourier series and Fourier transform. So first, let's talk a little bit about moving average. A moving average is the indicator that shows the average value of a security's price over a period of time. When calculating a moving average, a mathematical analysis of the security's average value over the predetermined time, and we may have several types of moving average, such as simple moving average, exponential moving average, triangular moving average, and it can be calculated on any data series such as open, high, low, close, volume, and etc. A buy signal is generated when the price rises above the moving average, and the sell signal is generated when the price goes lower and below the moving average. And this is an illustration. Now let's see how we can use Fourier series. So first, let's talk about signals and vectors. A dot product of a vector x and vector f and vector x is defined as the absolute value of f times the absolute value of x and times the cosine of theta, which is the angle between the two vectors. We can express f in terms of x. So f can be expressed as c times x plus e. So c times x is the projection of f onto x, and the error is smallest when the vector error e is orthogonal with x. So when the error vector is orthogonal with x, then we have the smallest error. So starting from here, multiply both sides with absolute value of x, then pull c out, we get c. Similarly, a signal can be expressed in terms of another signal. So f of t can be expressed as c times x of t and c, and then this is an approximation, and c is a coefficient that just like we already saw previously with vectors, and the error is the difference between f of t and c times x of t for t between t1 and t2 and 0 otherwise. So we select t such that we select c such that the error is minimal in terms of energy. So the energy EE is the integral of the error squared dt with the integral from t1 to t2, and replace E by f of t minus c times x of t, we get to this, and then taking the derivative of the energy with respect to c and let it equal to 0. We solve for c and we get c. And in the denominator we have the integral of x squared dt from t1 to t2, and this is actually the energy of the signal x. So with vectors, f is orthogonal with x when c is equal to 0, and with signals, f is orthogonal with x when c is equal to 0 as well. And this is because we have this in the previous slide, the integral of f of t times x of t dt from t1 to t2 is equal to 0. Now we talk about signal representation by an orthogonal signal set. First we talk about vectors. A vector in terms of mutually orthogonal vectors x1, x2 and x3. So first, if we express a vector f in terms of x1 and x2 approximately, then we can also write f as in terms of x1 and x2 with some coefficients, and then we add an error term at the end, and the error is the difference between f and the sum of c1 times x1 plus c2 times x2, which is the linear combination of x1 and x2. And if we use three orthogonal vectors x1 and x2 and x3, then f's can be fully expressed in terms of x1, x2 and x3. And here xi times ci times xi is the projection of f onto xi, and it can be calculated as you can see here. And finally we get to this step, and I here is actually the subscript. Similarly, a signal f of t can be expressed in terms of signals x1, x2 and x3, and they are called the basis signals. And the basis signals are orthogonal. So if we take the integral from t1 to t2 of the basis signal xm and the basis signal xn dt, then it would be equal to 0 if m is not equal to n, and it is equal to the energy of the signal if m is equal to n. Then the signal f of t can be expressed in terms of x1, x2, etc. up to xn. This is xn of t. This is cn of t. And finally, you can express that using the sum notation. We can rewrite this using the error term. So error term is the difference between the signal f of t and the sum. And also, just like what we saw in the previous slide, we can get the coefficient Cn. The coefficient Cn is the integral from t1 to t2 of f of t times xn of t dt from t1 to t2 divided by the integral of xn squared of t dt from t1 to t2, and the denominator is actually the energy of the signal. So we have En, and finally this is what we need for the coefficient Cn. Now we talk about the trigonometric series. Let's say if we have a signal set with cosine functions or cosine signals and sine signals. So number one here is actually cosine of 0 omega naught t. So cosine of 0 omega naught t, cosine of omega naught t, cosine of 2 omega naught t, etc. And then on the other side we have sine of omega naught t, sine of 2 omega naught t, etc. So we can use the signals as the basis signal. It is because they are orthogonal, and we can prove this. So the integral within one period of cosine of n omega naught t times cosine of m omega naught t dt is actually equal to 0 if m is not equal to n, and it is equal to t naught divided by 2 if m is equal to n. Similarly, we can look at this. This can be proved easily, and from here we see that the cosine functions are orthogonal to each other, and the sine function are also orthogonal to each other. And from here we see the sine and cosine functions are orthogonal to each other. And this can be proved easily if you take the reminder here in mind. So basically, if you use that trigonometric functions as the basis function, you can express a function f of t in terms of cosine and sine functions like this. And the coefficients for the cosine function with the frequency 0 is a0. The coefficient for the cosine function with omega naught as a frequency is a1, etc. We have a2 and a3, etc. And then on the other side we have b1 for the first sine function, and b2 for the second sine function. If we rewrite this as a0 plus the sum of a n times cosine of n omega naught t plus bn times sine of n omega naught t, and a sub n can be calculated, and it is equal to the integral from t1 to t1 plus t0, which is actually the integral within one period of the signal f of t times cosine of n omega naught t dt divided by the integral within one period of the basis function cosine squared of n omega naught t dt. And if n is equal to 0, then this is a special case. Then we get a naught, and otherwise if n is not equal to 0, then we get a n, other coefficients. And similarly, you can get bn. So from there we can get to another form, which is the compactor form, by pulling the square root of an squared plus bn squared out, and then let this and that be cosine of theta n and sine of theta n. Then we get to this form. And Cn here is actually the square root of an squared plus bn squared. And the expression inside the square brackets is actually cosine of n omega naught t times omega naught t plus theta n. And finally we get to this, and C naught here is actually equal to A naught. And on the right side we have the relation between Cn and An and Bn, theta n and An and Bn. And next we talk about the exponential Fourier series. The exponentials e to the j n omega naught t is orthogonal over the period t naught, and it can be proved easily. So for any m which is not equal to n, then the integral of or you can say the inner product of an exponential and another exponential is always 0. So the exponentials are orthogonal to each other. A signal f of t can be expressed as the exponential Fourier series. So f of t can be expressed as the sum of the coefficient dn times e to the jn omega naught t. And n can be from negative infinity to infinity. And the coefficient dn is equal to 1 divided by t naught times the integral of the signal times the e to the negative j n omega naught t times dt, and the integral is within one period. And this is the relation with the trigonometric series. So starting from the compacted form of f of t, using the Euler's formula, you get to this, and we put e to the j times theta n and e to the negative j times theta n out, and we get that term, and we call the first term dn, and the other is d negative n, and rewrite this. You get this, and we get this. For n from negative infinity to infinity, and c naught now is equal to d naught. Now let's talk about Fourier transform. So previously we saw a signal expressed in terms of exponential Fourier series. And the coefficients dn can be calculated using this integral. Okay, now we make the integral f of omega, which is a function of the angular frequency. So if we call f of omega the integral from negative infinity to infinity of f of t times e to the negative j omega t dt, then this integral now becomes f of n omega naught, and this is a new form of the coefficient dn. And then you can rewrite f of t within one period. This becomes this form, and here we just replace dn, right? dn. So this is a new form of f of t within one period, and as t naught approaches infinity, the angular frequency omega naught approaches 0, and f t naught approach f of t So the function of the signal within one period approaches the function wholly f of t. Then we use delta omega instead of omega naught, and just plug in the formula that we saw in the previous slide. And then they take the limit. You take the limit of the function f of t within one period. Let the period approach infinity. Then we get to this form. So the sum becomes the integral f of n times delta omega becomes f of omega, e to the jn times delta omega becomes e to the j omega, and also t. So this is the inverse Fourier transform. And f of omega previously we had in the previous slide is the Fourier transform. And on this slide we have the Fourier transform table. The first column shows the a function in the time domain, and the second column shows the function, the corresponding function in the frequency domain. So if we have a function in a time domain, then we look at the second column in the frequency domain, and this table helps, and you don't have to calculate the Fourier transform manually. And also this slide shows the property table of the Fourier transform. And for now we just know that we have it here, and later on we will go back to this. Now we talk about the sampling theorem. So let's say we have a function or a signal f of t in the time domain, and let's say in the frequency domain we have the spectrum, which is the Fourier transform of f of t, and we call this f of omega, and f of omega looks like this. And here we use both axes. One is for the angular frequency and the other is for the regular frequency in terms of hertz. And the bandwidth, which is the distance from the origin to where the frequency, the spectrum becomes 0, is the bandwidth. So you have B on the Hertz axis, then under the regular frequency axis, then it is 2 pi times B on the angular frequency axis. So in order to for the computers to process the signal, then we need to sample the signals. So in order to do so, we use let's say an impulse chain. The impulse chain contains multiple impulses. So taking the impulse chain delta of t and multiply that function with f of t, what you have is here. And this is the sampled signal f of t. So the sampled signal f bar of t is equal to f of t times the impulse chain, which is delta of t. The Fourier transform of the sampled signal f bar of omega looks like this, and basically we take the spectrum of f of omega and repeat it at every omega s. And omega s here is the sampling frequency. On the angular axis, on angular frequency axis, we have omega s, and on the regular frequency axis, we have fs. The impulse chain can be expressed as a trigonometric Fourier series, and this can be proved. So the sample signal, which is the product of f of t and the impulse chain, can be calculated, and you can see it here. And now the cosine function is actually the sum of two exponential, one with the power jn omega st, and the other with the power negative jn omega st. And this is the Euler's formula. And taking the sum divided by 2, you get the cosine term. And if you change this to negative, you change it to the negative side, then you get the sine term. So from here, multiply both sides with f of t, you get this. And then taking a Fourier transform of both sides, then on the right side, the Fourier transform of this term becomes f of omega minus n omega s, and the Fourier transform of the other becomes f of omega plus n omega s. And you can look at the property table for the Fourier transform, and finally we get this. And that's why the spectrum of the signal is repeated on to both sides on the Fourier transform plot for f bar of omega. If the if fs, which is the sampling frequency, is greater than or equal to twice the bandwidth, so b is the bandwidth, then we can reconstruct the signal f of t, and 2b, which is twice the bandwidth, is called the Nyquist rate. Let's look at the example. Given a signal, this is sinc function, and from the Fourier table, Fourier transform table, we get this. So the Fourier transform of a sinc squared function is a triangle function in the frequency domain. This is a sinc squared function, not sinc, sorry. And then we take the samples of the function, and we take a sample here and there and there and there and there and there, etc. So the interval between samples is 0.2 seconds. So from there, the sampling frequency is 5 Hz, which is 1 divided by 0.2. Now look at the spectrum of the sinc squared function. From here we can see that the bandwidth is 5 Hz. So okay, here b is now equal to 5 Hz, and the sampling frequency is also 5 Hz here, and the requirement says it should be 10 Hz at least instead. So looking at the spectrum of the sampled signal f bar of omega, so the spectrum, basically we take the spectrum of f of omega, right, and the height is equal to the height in f of omega, but divided by t, as we can see in the previous slide here, right? So we have 0.2 here. Okay, and divided by t, we get 1 there, and we repeat the spectrum at every ten pi, right? At every 10 pi, or actually at every 5 hertz, same thing. And looking at the plot, we see the switches are overlapping. And in this case, we cannot reconstruct the signal FFT completely. Now, if we take the samples at exactly the Nyquist frequency 10 Hz, so as you can see here, the samples are taken at every 0.1 second, and 1 divided by 0.1 is equal to 10. So 10 Hertz is the sampling frequency, and looking at the corresponding Fourier transform of the sample signal, and we repeat the spectrum of f of omega at every 10 Hertz. At every 10 Hertz, one is there, the next one is there, and the next one is there, and next one is there, etc. And of course the height is divided by the period t. So looking at this, we see that the spectra are not overlapping, and in this case we can reconstruct the signal f of t completely. And in the case of oversampling, when the sampling frequency is higher, or even much higher, for example 20 Hertz, when the interval between samples, the interval between samples, between the adjacent samples, here is 0.1. I'm sorry, 0.05 actually. So 0.05, 0.1, 0.1, 15, and 0.2. So 1 divided by 0.05 is equal to 20 Hertz. And now look at the Fourier transform of the sample signal, and the spectra are not overlapping, because here we have one at 0 and this one and the next one repeats at 40 pi or at 20 Hertz. If you draw license for a regular frequency into Hertz, then this is 0, and that is 20 Hertz. And in this case, we can easily reconstruct the signal f of t. And for signal reconstruction, so if we put a filter, in the frequency domain over here to capture the spectrum that's at frequency 0, then we can use this to reconstruct the signal. And if in the frequency domain, if the Fourier transform of the filter is actually a rate function, and taking the inverse Fourier transform, you get a sinc function, and this is the inverse Fourier transform of the filter in the time domain. So in the time domain, when we reconstruct the signal, we take the convolution of the samples and h of t, which is the inverse Fourier transform of the filter. So this is the formula for reconstructing the signal, and it's also the convolution sum of f of k times t times h of t minus k times t, and the h function, which is the inverse Fourier transform of the filter, is a sinc function. And graphically speaking, we superimpose multiple sinc function. So for example, one is there, and one is there, and another one is there. So we superimpose multiple sinc functions altogether, then the sum would give us the reconstructed signal f of t. Now we talk about the discrete Fourier transform DFT. So numerical computation of Fourier transform requires a samples value of the function f of t, as computers work only with discrete data. And computers compute the Fourier transform f of omega at some discrete values of omega, and we need to relate samples of f of omega to samples of f of t in the time domain. So given a signal f of t, taking the Fourier transform, we get f of omega. And previously we saw that if we take samples, of f of t, and we take the Fourier transform of the samples, then correspondingly in the frequency, we repeat the spectrum of f of omega at every fs, at every sampling frequency, or if we use the angular frequency, then it repeats at every omega s. And the dual time sampling theorem says that if we sample in the frequency domain, then correspondingly we repeat the spectrum. We repeat the signal in the time domain. And we repeat that at every t0. And t0 is actually 1 divided by f0. And f0 is the difference in terms of frequency between two samples in the frequency domain. And okay, and if we take samples, in the time domain of the repeated signals, so if we take samples of the signal and taking the Fourier transform, then in the frequency domain we repeat the spectrum of FFT. I'm sorry, f omega. So we repeat that at every fs. And due to the dual sampling theorem, then if we take the samples in the frequency domain and taking the inverse Fourier transform, then we repeat the sample signal in the time domain. And repeat that at every t0. And t0 is 1 divided by f0, and f0 is distance between two adjacent samples in the frequency domain. And if we call t the interval between two samples in the time domain, then in the frequency domain fs, which is the sampling frequency, is 1 divided by t. And we can prove that the number of samples and not in the time domain is equal to the number of samples in the frequency domain and not prime. The discrete Fourier transform, or we call DFT, relates samples in the time domain and the frequency domain. And here f of kt is the kth sample of f of t, and f of all omega is the all sample of f of omega. and the sampling frequency is chosen such that the sampling frequency is greater than or equal to twice the bandwidth. And this is the frequency revolution f naught. F naught is equal to 1 divided by t naught, and the number of samples of the signal n naught is equal to t naught divided by t, and we saw those in the graph. So if we define w n naught and using the exponential e to the negative j 2 pi divided by n naught, and it is equal to e to the negative j omega naught, and the pair of the Fourier transform becomes this. And the exponential becomes w kr and not, or so we call w and not to the kr is the power, and w and not to the negative kr. And computer algorithms use the fast Fourier fast Fourier algorithm to compute the discrete Fourier transform. So if we split the expression for fr into two parts, the first part is the n naught divided by 2 point sequence of even samples, and the second is the n naught divided by 2 point sequence of odd numbered sample. And then we have this omega, w n naught divided by 2 is actually equal to w n naught squared. So bring that in, then we get this, and we name the first part gr and the second part hr. And we can prove that gr plus n naught divided by 2 is equal to gr, and hr plus n naught divided by 2 is equal to hr, and this is n naught divided by 2 periodic. So and finally we can get to this, and that says fr plus n naught divided by 2 is equal to gr minus w n naught to the r times hr. And this is how the first and not divided by 2 points are computed. So FR is equal to GR plus WN naught to the R times HR. So GR is here and HR is there. So FR is equal to GR, right, plus HR times WN naught to the R, and the last n not divided by 2 points, FR plus n not divided by 2 is equal to GR, right, minus HR times or you say plus HR times the negative W and not to the R. And we repeat the same procedure by dividing GK and HK into n naught divided by 4 sequences corresponding to the even and odd number samples until reaching 1 point DFT. So for example, with 8 point FFT, so with 8 point FFT on one side we have time samples from F0 to F7, and on the other side we have frequency samples from F0 to F7, and F0 is equal to G0 plus H0 times the width and similarly F1 can be computed from G1 and H1, etc. So that is the first step. In the second step, we we look at n naught, which is equal to 4 points DFT. And from there we get to this and to that. And in the next step we look at 2 points DFT, and we get this and this and this and this.